Good day, everyone. Welcome to ME 160, and this is the first lecture for vibration absorbers. So, we have tackled at this point two kinds of vibration control, and this will be the last. And our objectives for today would be threefold. The first is we have to distinguish how vibration absorbers actually protect our systems. Next, we want to distinguish particular properties of our system independent of one another and properties when the absorber is connected to the system to protect. And the third and the last one is to understand how damping affects the absorber performance itself. So, getting on it, here are some examples of vibration absorbers. This one is not typically brought up when it comes to vibration absorbers, but if you have been traveling along the highways next to high voltage lines, you may have seen these. These are kind of weights that are hung from high tension cables. So these high tension cables, they carry high voltage power essentially from one end of the region to another. And the problem for their use is that when high winds blow, so when high velocity winds blow over them, they tend to get very rickety. And to get rid of the vibration on those cables and to avoid the risk of them breaking or essentially being torn apart by the wind, you have these vibration absorbers called stock bridge dampers. So stock bridge dampers, they absorb some of the energy from that shaking to ensure that the cables do not shake too much or they don't exceed a particular vibration characteristic. When it comes to vibration absorbers, though, they are most famous for being used in structures. So here, we have the Shanghai Tower Chun Mass Damper. So it is the centerpiece in this picture. Some construction companies, they really do turn their Chun Mass dampers into a work of art. The cover image of this slides are is actually the Chunma Stamper of Taipei 101. That is the more famous TMD. This one is also a work of art and it's found in Shanghai, China. But most Chunma stampers are actually boring looking, just like this TMD under the bridge. And the purpose of these is, of course, to absorb shaking from earthquakes, from unintended geological phenomenon that could damage the structure if unabated. So the name itself alludes to the method of protection. When it comes to comparing an unprotected and a protected system with an absorber, here's what it looks like. So if you have a base excitation, your system is kind of okay, so it's vibrating a little too much for my comfort. And if you insert or install a vibration absorber that is tuned just right, you can get this particular performance. The absorber kind of absorbs, quote unquote, most of the shaking, such that the primary system doesn't really experience much at all. So that is how vibration absorbers protect your systems. Now, okay, so here's a question. Knowing that I also have the option of installing vibration isolators. So take note, the first kind of vibration control that we learned is vibration isolation, essentially adjusting the spring and damper that's connecting the system to the ground. Why not just use that compared to an absorber? So that is a good question. One reason you might want to avoid vibration mounts and go for the absorber is that the stiffness and the damping properties of the system to the base cannot be altered without causing some significant performance degradation. Like for example, if you have a building and you want to protect that building from earthquakes, so it's possible that you can change the way the building is mounted and it will be protected. However, that could cost some enormous amount of money, or it could cause the structure to easily fail against the more basic engineering principles, like for example statics, that could make the structure vulnerable to that. So there might be instances wherein it's better if you just install a new part or an addition to the system and then tune it such that it will protect the system uh, with no need to change anything about its foundation, its mounting, etc. So that might be a use case for the absorber, but that's something that can only be answered by a vibration engineer or a civil engineer in this case. So, when it comes to vibration absorbers in ME160, we're only looking at this particular model. So, this comparison from practical engineering, his YouTube videos are actually very good, demonstrates how vibration absorbers dissipate the energy from a base excitation. But for ME160, in our case, we will model, or at least we will look at circumstances wherein the forcing function itself is connected to the primary system. So again, in ME160, we will examine absorbers wherein the disturbing function or the forcing function itself is connected to the primary system. We will not go into the instance wherein the base itself is performing some amplitude shaking. So yeah, keep that in mind. Now, all right. The next step in this is, of course, if we want to understand what properties, what mass, what stiffness, or something else about our absorber to use, we have to look at the model of our system. And of course, we start with the system that we want to protect. So here is our primary system. So this is the machine or the mechanism or the complex that we want to protect. And we label all of its properties with the subscript P for primary. So you have a mass, primary mass MP, you have a stiffness KP. And this system has its own natural frequency that is of its own. So that is, we will label it as omega p in this case. So this is the natural frequency. We just drop the n so that we can essentially label things faster. So now you might ask, okay, so which forcing frequency is the most dangerous to the primary system? Of course, if you have learned anything in ME160, so as long as there is no damping, the most dangerous forcing frequency omega for this kind of system is, of course, its own natural frequency. So again, this is the most dangerous as long as there is no damping for this. Next, all right. So we will now look at our absorber outside of being connected to our primary system. So this is just our absorber on its own. It has its own mass, it has its own stiffness, and of course, it has its own single degree of freedom, natural frequency. And we will, of course, shortcut that to omega sub A. Now, the big question with absorbers is that, okay, so I have a mass, I have a stiffness. The natural frequency of this entire system connects M and K. So the question of, okay, what mass, what stiffness do I use can be simplified into asking, okay, what frequency should my absorber have to protect my primary system? Okay, so the primary question for absorbers is what frequency of the absorber should I have to protect my primary system? Now, to get there, we have to model this now as a 2 degree of freedom system. So when we have a 2 degree of freedom system, we have a very complex interaction. And fortunately, this one is similar to one of our models in chapter 6 for 2 degree of freedom systems. And if you look at our equation of motion, it is simply just that. So M here is M sub P. So I forgot the subscript. M sub P. This one is M sub A. This is the acceleration vector. They call that, since we are looking at a condition of forced response, our greatest interest is in the steady state amplitudes. So this one is the steady state amplitude of the acceleration, and this vector, this displacement vector, is the steady state amplitudes of the primary system and the absorber. All right, so this is our stiffness matrix as well, and this is our forcing matrix. Again, if you look here, the forcing function is applied only to the primary system, so it's only in the first row. And if you notice, our stand-in for the forcing function is only the forcing amplitude. So forcing amplitude, displacement amplitude, acceleration amplitude. So this is only possible because we are only looking at the steady state response of our system. Now, to move things along, we combine these two terms into a single matrix. So this is our characteristic equation, and here is our impedance matrix. So we have our stiffness minus m, this mass matrix, times omega squared. Now, since our interest here is the displacement amplitude, we can get that by taking the inverse of this impedance matrix and then multiplying it to the forcing function. I will not bore you with the derivation, but that results in the following steady state amplitude formulas. So this is what we have. So XP is the displacement amplitude of our primary, and XA is the displacement amplitude of our absorber. So what you notice first, so if you look at our equations, the one thing that we want to pay attention to is actually XP. And if you look at XP, we notice that there is a product. There is a numerator factor that is essentially a difference of two terms. So because there is a difference in two terms, we can actually make XP to 0. So how they do that? So how they make our amplitude for our primary system 0? So we take this factor, this difference, and then equate it to 0. And that gives us the following relationship. So in order to completely kill the vibration of XP at the forcing frequency omega, our omega A must equal the forcing frequency. So take note, a tuned vibration absorber will have its absorber frequency equal to the forcing or the disturbing frequency. And this is the be all and end all, or at least the core of vibration absorber tuning. So omega A must equal omega at all times. All right. So that is the thing that I wanted to emphasize. Now, since we have amplitudes, we can also normalize these. We can get the primary system magnification. So it's just F naught over K sub P, and we get this relationship. Now, if you notice that this will get messy if we do not simplify the fractions. So we will define new terms. For example, we have a term for the ratio of the absorber mass to the primary mass. So that is the mass ratio indicated by the Greek letter mu. Now, Greek letter mu is kind of a good indicator of how good your absorber is, because of course, let's say you have a very tall high-rise condominium and you want to protect it against magnitude 8 earthquakes. Now, you don't want the absorber of that building to be as heavy as the building itself, because the building will need to have more steel, more materials just to support that absorber. So if you look at the construct of this model, though it's simplified, you can notice that the absorber is hanging from the primary system. So the building has to support the absorber mass as well. And if this mass is too much, like if it's equal to the building's mass or the primary system's mass, it's gonna fail on different engineering principles aside from vibration. So yeah, we prefer the mass ratio to be less than 1 and very small actually. We will tackle that in the next meeting. The next ratio that we can define is the ratio between the primary system's natural frequency and the absorber system's natural frequency. And that is beta. So beta is the single degree of freedom frequency ratio. Now, if you square beta, you can unleash K and M for both absorber and the primary system. And if you move terms, you actually get the expression for the ratio of the stiffness, Ka over Kp. And that is the mass ratio times the frequency ratio squared. By doing so, you can get some simplification. So here's the simplified primary system magnification. Another simplification that we can tackle is frequency ratios. Because there are two frequencies that we have defined, we get two frequency ratios. So the first is the primary frequency ratio, which is just the forcing over the primary. So it's R sub P. And we get the absorber frequency ratio, which is R sub A equal to forcing over the absorber frequency. And by substituting these terms, we get this very simplified form for the primary system magnification. So as you can see, you have a denominator, you have a numerator. Your numerator is still it still has a factor of a difference. So it's 1 minus RA squared. And here is your absorber magnification. So if you notice here, the absorber magnification is not XA divided by F naught over KA. It's XA over F naught divided by the primary stiffness. So that is something that you have to look out for. So right, here is where we will be playing around most of the time. We will go to X sometimes, but MP and MA is usually tends to be useful. Now, before we proceed, we have to make distinctions between the individual components and the combined system themselves. So on their own, the primary system has a unique natural frequency, and so does the absorber. Now, if you combine the absorber to the primary system, something happens. And what happens is that the natural frequencies of this combined system is completely changed. So again, when you combine these two systems, the absorber to the primary, the natural frequency of the overall system is completely changed. So what does this mean? If my frequency omega hits omega p at this point, it will not trigger infinite magnitudes or infinite amplitudes. So that is the difference. And my new infinite amplitudes will be positioned at different and distinct natural frequencies from what I originally had. Here is a useful chart to separate things out. So again, if you have your primary system and your absorber as separate entities, they have their own properties. But once you combine them into a 2 degree of freedom system, they get new natural frequencies and they get new behaviors as well. So the SDOF frequency ratio is the one that connects the two individual properties. So beta is actually not demonstrated outright by the combined system, but it is useful in simplifying terms. So again, this is a distinction. Keep that in mind. Omega A and omega P are dangerous when the primary system and the absorber is being operated distinctly from one another. They are not connected. But once you connect these two, you get a totally different kind of behavior. So, okay, let's look at MP. So, our main concern with vibration absorbers is we want to minimize or kill completely, if possible, the amplitude of the primary system. And in doing so, we look at M sub P. So again, M sub P indicates to us that it is possible to completely zero out the amplitude of our primary system. And that condition is RA equals 1. So what is RA? It's omega over omega A. So that merely means that our absorber frequency has to equal the forcing frequency itself. So this is the primary goal of the absorber, if anything else changes, this one will stay the same. So again, the absorber frequency will always chase after the target forcing frequency. That is the key characteristic of the absorber. Next, if we look at our expression here, we also have a denominator. And if that denominator is equal to 0, we get infinite magnitude, of course. So this entire expression, when you equate it to 0, the solution for these will actually be the new 2DOF natural frequencies of our system. Again, this is distinct from omega A and omega P. So omega N1 and omega N2 will be something that you will have to calculate by analyzing this expression here. And usually for vibration absorbers, or at this point, I might switch over. Vibration absorbers is also another name for tune mass dampers, so or TMDs. So there are two typical conditions for them. It could be that the forcing frequency is the primary system's natural frequency itself. So this might be the case wherein you have a structure of or a mechanism that already works perfectly um, outside of the vibrational considerations. But because of its vibrational characteristics, the primary natural frequency is inside the operational bandwidth. So the omega that you have to kill is omega p itself. And because you have an absorber, omega A has to chase after omega. And so you get this kind of double identity wherein omega is equal to omega A equals omega P. And there are consequences for that. So first and foremost, your beta, your frequency ratio is reduced to 1, and all of your R's are essentially the same. So your equation simplifies to just this. This is the denominator, and you can easily find the natural frequencies if this is the case. Now, the second case, this is the probably the more common one, is if the omega that you have to kill is outside or not the same as your primary frequency. So this is your ideal case. So the primary frequency of your main mechanism is actually very far away, but the omega that you want to target is causing deleterious amplitudes that affect your operation. So in this case, the absorber's frequency will still chase after the disturbing frequency. So while the primary system is no longer coupled to omega, omega A will still chase after omega regardless. So when you have this kind of situation, you just have the generic expression. There is no simplification. You just have to go through it as is. All right, so let's look at the magnification now. That is our model. Let's graph it. So what we have here is our case one. So we assume that the primary frequency is the one that we want to kill, the disturbing frequency. So the absorber frequency chases after omega, which just so happens to be omega p. And this is our MP expression. All right. So let's look at the graph. So this is the primary magnitude and this is the primary frequency ratio. Our blue dashed line is our original primary system. And if you notice, it peaks at RP equals 1, which is resonance. If we follow the conditions such that omega A is indeed equal to omega, then we get the green graph. So this green graph is the behavior of our primary system with the properly tuned absorber. And if you notice that at omega equals omega p, or R equals 1, the amplitude of the primary system is completely gone. It's 0. That is amazing. And another thing that you have to note for the vibration absorption protected system. So this peak indicates our primary system's natural frequency. When we introduced the vibration absorber, we didn't eliminate the peak, rather we split it in two. Now this split causes two peaks, two infinite peaks, and those peaks happen on the values indicated below. So what are these values? Those values are the two DOF natural frequencies of your system. So these are the new dangerous frequencies that you want to avoid. Now, you can define your safety threshold as the, okay, so I just want to not operate exactly at these natural frequencies. So, okay, as long as I stay from 0.85, let's say, to 1.17 frequency ratio, I am safe. So that is one kind of criteria. Another safety criteria is by determining a threshold magnification value. So let's say, okay, at m equals 1, my system is safe. So if I want to locate a safe frequency range for my system, I will look for the region of my green curve here that is under the m equals 1 line. And this region here is what we call the safety threshold or the operational bandwidth. This is the frequency range wherein I see safe magnification values. Now, this value, or at least in ME160, we will limit MP or the safety value of our MP to 1. However, when you go out into the field, you might see MP values of 2, of 3, of 4, or 6. It really depends on the application. But for simplicity's sake, we will only limit ourselves for this course to MP equals 1. That means as long as my MP is equal or less than 1, then I can consider that safe. So this is the safe zone. So, all right. Now, okay, so this is the primary systems. What about the absorber? Will my absorber then take on the properties of my old system? So what I mean to say is, okay, if my system encounters omega equals omega A equals omega P, how will my absorber behave? Will it behave like, okay, it's the wildest possible shaking in R equals 1? So take a guess. So the purple curve here indicates the behavior of our absorber. And what you notice here is that the absorber also has a valley uh, inside R equals 1. But it's no longer equal to 0. And if you notice, the infinite peaks of our absorber coincide with the 2DOF natural frequencies. And that is because the absorber and the primary system are now connected. They are behaving as a new system that has its own shared properties. So if you look here again, the absorber at R equals 1 or at the frequency that it wants to kill is not at its peak amplitude but rather at a valley that is non-zero. So if you think here, if you're operating your system here, your primary system is not shaking all that much, but your absorber is shaking like so, like this. But if you move a little to the right, your primary system starts to shake and your absorber system starts to shake a little more wildly. So that is the distinction. All right, so yeah, that's how the vibration absorber protected system behaves. As long as you stay in this zone, you are okay. Or as long as you don't encounter these frequencies that cause infinite peaks, you are okay. And you might have realized, okay, so what about damping? What if we introduce damping to our tune mass dampers or vibration absorbers? This is where it gets a little more complicated. Because if you go to our chapter 6 module again for degrees of freedom systems, you notice we completely skip the damped 2DOF system. And there is a good point for it because if you take the impedance matrix of that, you get an imaginary term from the damping expression itself. And if you want to get the principal or the primary system size rate amplitude for this case, you get this complex behemoth here. Okay, can we do this? Actually, we do have, we require some high algebraic Hubalu, high algebraic parkour, but we'll get there. The first thing that we have to recall is that we have to use our ratios to the T right now. So here are our established ratios from before. So you have our mass ratio, we have our frequency ratio, and we have our primary frequency ratio here. We're going to add a fourth one. This is called the mixed damping ratio. Now, don't be fooled. The mixed damping ratio is nobody's damping ratio. So I want to make that clear. The mixed damping ratio, the zeta mix, is nobody's damping ratio. Because if you look at the expression, you have properties from the absorber, but you also have properties from the primary. This makes this a very messy damping ratio. So uh, zeta mix is just a convenient fraction because this ratio will show up a lot in the derivation of the final expression for MP for damped cases. So again, this is just for convenience. Zeta mix is just for convenience. It is nobody's damping ratio. So another thing that we can do is to assume that, okay, since our system is experiencing such wild vibrations, let's assume that our primary system's damping is essentially non-existent. It's negligible. So we apply some particular complex identities and we eventually get to this. So this is our primary magnification with damping, and this is our absorber magnification, I mean, with damping. So it's a lot more complicated. So how did we derive this? You can check the appendix of chapter 8. I do not expect you to understand what happened to that mess of a derivation, but just you know that we end up with this particular curve. Okay, so I have a curve. I want to know how it behaves. So that's the more important one. How does this formula behave? Do I see a zero value for my magnification? Do I see an infinite value for my magnification? So okay, let's see. What happens if I increase zeta mix by just a little? This is the effect. So green was what we had before, no damping. And now this kind of fuchsia colored or magenta colored curve is one with a little bit of zeta mix. So what do you notice? The first is your peaks are no longer infinite. And that is great. That is super great. Since you have no infinite amplitudes, there is a potential wherein uh you can make all of your range here to be safe. But we'll talk about that later. So we have our pro is that we have infinite amplitudes. Our con though, if you look at the valley, our magenta curve is not touching zero anymore. So we don't have infinite peaks, but we also have no zero amplitudes. We just have a minima in the middle. So that is our trade-off. Now, if you want to see what happens to to the curve, to the primary system amplitude as you increase zeta mix, here you go. So the darker the curve, the more the damping it has. And if you notice, the curves kind of peter out, but eventually, from two peaks, you get this one single peak here. So it's kind of a very odd behavior. Um, why does it behave that way? That is not within the scope of our course, but it is interesting actually. And another thing that's interesting is if you look at the four curves here, they all intersect at two particular points. So regardless of zeta mix, they will always intersect at these two particular points. Why take interest in this? So let's say your safety MP, your safety primary magnification is not limited to one. So this vertical line is not limited to just this. Let's say it's a little higher. Let's say it's 10. And you want it such that all of your entire range, your entire frequency range, your entire curve here is below that safety value. Is it possible to tune the damping such that you get such a value? So yes, it is possible. And two particular people theorize that if these two intersection points are the highest points, as in if these are the peaks of this particular curve, then you get something of an optimized Chun mass damper or an optimized vibration absorber. So who are these? These are Ormond, Dredd, and Dan Hartog. And if you notice, do not be bothered by the year because this kind of relationship is still used for this application. So even though it was almost 100 years ago at this point, this particular relationship for the frequency ratio and the zeta mix ratio is still relevant up to this point. So if you notice, this optimized beta, this optimized zeta mix is only dependent on the mass ratio. So if you know the mass ratio that you want, so let's say I want my absorber mass to only be 10% of the mass of my primary system. And by saying that, you actually get one value of an optimized frequency ratio, and you get immediately a optimized mixed damping ratio. So this simplifies things. You might want to ask, okay, how did this expression, this set of expressions came about? Again, that is not the scope of our lecture. Just know that these two engineers did the hard work for us and defined that this is what triggers the optimal conditions. Okay, so if this is the optimal condition, let's see what it looks like. Ta-da! So if we have a mass ratio of 10%, our optimized beta is 0.909 and our optimized zeta mix is 0.1679. And if you look at this curve, ooh, okay. So now the intersection points, if you're confused, what are these dashed lines? These are the dashed lines for different values of zeta mix. So they have the same mass ratio, they have the same frequency ratio, but they have different zeta mixes. And all of these dashed lines or these dashed curves, they still intersect at these 2 points. And let's say, okay, so what is the implication of this? So if my initial threshold was okay, so if I just want magnitude less than 10, if you see here, it's possible to actually have an entirely safe frequency ratio here, or frequency range, I mean. So if initially we said, okay, I want a primary magnitude of 10 or less, and I will declare that safe for my system. If you look here, all of your range is essentially safe. And that is the beauty of the optimized Chron mass damper. Now, if you look at this curve, there is no way that this value is touching zero. If we maintain MP must be less than or equal to 1, this is in no way safe at all. So, safety depends on the definition of the safety threshold criteria. Because for ME 160, we will keep MP less than or equal to 1 as our safety criteria. You might not see this all too much. So what you just need to remember is that there is an optimized beta and a zeta, and that is all to it essentially. So okay, I may be saying, okay, can we get on to solving now? Can we try out some problems? Yes, and that will be the point of our next meeting. So I hope that we can be able to meet on that day in person because this will be a doozy. Okay, thank you so much.